first section of Chapter 7, Section 7.1, will introduce us to what an exponential function is. We'll talk a little bit about exponential growth and exponential decay, the difference between those two different types of models. And we're going to attempt to be able to write and evaluate exponential expressions, model growth and decay problems. So here we go. First, what is an exponential function? Very simply, an exponential function is one of the form, I could say f of x equals a times b raised to the x. Examples of this might be like f of x equals 3 times 2 raised to the x, or sometimes you just see like 5 raised to the x. It doesn't have to have visually have an a and a b. Here this is the same as 1 times 5 raised to the x. So sometimes there's an a value there even though it doesn't look like it's there. Non-examples, real quick, just because it's important to distinguish between what an exponential function is and what it isn't, because you see the word exponent and you think, well, something with an exponent is an exponential function like x squared, and that's not correct in this sense. The exponent specifically has to be the independent variable x. That's what makes this an exponential function. So when the x is located as the power, as the exponent, that's an exponential function. When the x is located in the base, then it's not the exponential function. Let's look at the graphs of a couple of exponential functions, and this will kind of lead us into the describing what exponential growth and exponential decay is. We won't spend a whole lot of time graphing functions, especially graphing exponential functions by hand. We'll use the graphing calculator to do it some, but I think it's an important exercise just so you can see the shape of one of these functions kind of to begin with. So let's just pick some values in our table. Why don't we start with 3, 2, 1, 0, -1, -2, -3. So for the y value here, I want 2 raised to the third power. That'd be 2 times 2 times 2, that would be 8. So that's a 0.38 on our graph. 2, that would be 2 to the second power, that's 4. 0.24 on our graph. If we put 1 in for x, we get 2 to the first, which is 2. So that's 0.12. I put 0 in for x, 2 raised to the 0 power is 1. I put -1 in for x. -1 in for x, let me actually show the work here. If I have 2 raised to the -1, that's the same as 1 over 2 to the +1, or 1/2. Put -1 in, you get 1/2. If I put -2 then the same sort of similar thing happens. We'd get 1/4. If I put -3 in, we get 1/8, and this is just getting smaller and smaller and smaller. In fact, it's going to keep getting closer and closer and closer to the x-axis as it goes out to the left. But it's never going to come beneath, at least this graph is never going to come beneath the x-axis. So if I were to draw this, it looks kind of like this. Exponential functions typically have this kind of shape, and they're characterized like this. They typically flatten off on one end, and the other end will typically kind of shoot up, and it'll go up fast. It goes up much quicker as it continues to go out to the right. Okay, another example. Let's do the same thing. Let's make a table of values for this particular graph. I might do the same values, maybe 3 to -3. That should give us a pretty good idea. I have -2 times 1/2 raised to the power. If you're not sure on the mental math, I'll just kind of do one here on the calculator just so you can see that we can do it this way. Hopefully you can see the calculator screen. I could type -2 times 0.5 raised to the third power. Gives me a value of -1/4. So I'm at 3, and then now we're 3, -1/4. About there. Okay, if I plug 2 in, so we have -2 times 1/2 raised to the second. I get an answer of -1/2. If I put 1 in, it'd be -2 times 1/2. That's -1. I put 0 in, that's -2 times 1/2 raised to the 0. Well, the 1/2 raised to the 0 is 1. -2 times that 1 is -2. If I put -1 in, we'll get -4. If I put -2 in, we'll get -8. When I put -3 in, we get -16, but we're starting to go off my graph here, and so this exponential function looks like this. You see sort of the same characteristics as on the last graph, in that it will flatten out towards one side, and well, the last one went up, this one's shooting down, but in either sense, it's going to flatten out on one side, it's going to go towards either positive or negative infinity on the other side. Okay, having seen a couple of graphing exercises, I think we're ready to describe what exponential growth and exponential decay are. Exponential growth would be when the function, I'll say the function is increasing. What does increasing mean? It means going up from left to right. Okay. The first example is one like that. The first example that we did, where we had our graph and the graph went like this. That was exponential growth. As I read my graph from left to right, it is going up. It's increasing. On the other hand, then, exponential decay is just the exact opposite. The function is decreasing. Decreasing meaning that it's going down from left to right. Now that second example we did didn't show this. So typically what a graph of a exponential decay model looks like would be one that does this. It's going to come down the graph from left to right. Now, our next type of exercise that we're going to be interested in doing is can we write exponential growth and decay models? So typically, like modeling a story problem, an application problem with an exponential function. And so we have an exponential growth or decay model. Looks like this. A of t, it's like my function f of x, equals a times 1 plus or minus r raised to the t power. Defining the variables, the little a is the initial amount, the r is the growth or decay rate. Use plus if the problem is describing growth, use minus if the problem is describing decay, and the t is just simply your length of time. Sometimes we have a length of time and we want to know how much of something we have after a certain amount of time. Sometimes we know how much we have and we want to know how long did it take to have that certain amount. This first example says Clara invests $5,000 in an account that pays 6.25% interest per year. How many years will her investment, after how many years will her investment be worth $10,000? So let's start with that exponential model. A of t equals a times 1 plus or minus r to the t. And so we have a of t equals, our initial investment was $5,000. Now, it's time to choose plus or minus. We are putting this money in an account, and the money in the account is growing from 5,000 to 10,000. So this is an exponential growth problem. We'll use plus. Our interest rate is 6.25%. That's 0.0625 as a decimal raised to the t. So our model A of t equals 5,000 times 1.0625 raised to the t. So there is our model. Now what this model can solve for us is it'll tell us how much money is in our account. If little a was the initial amount, then big A is the final amount. How much money is in our account after t amount of years. I want to know how much do we have after 2 years. I put 2 here and evaluate this. Or after 5 years, I put 5 here and evaluate this. Now this particular problem is not giving us a specific amount of time. It's giving us an ending amount of dollars. We want to know how long did that take. So we're going to rewrite the model now to say our final amount, 10,000, equals 5,000, 1.0625 to the t. So we have an equation now that we need to solve, and right now we lack the ability to solve this equation algebraically because it comes later in the chapter when we learn the math that can solve this. So right now what we're going to do is solve it graphically. We're going to use our graphing calculators to do this. So let me bring mine in and I'll kind of show you how we can do this on the calculator. First thing you're going to do is go to the y equals screen. We're going to let this side of the equation be the y1, this side be the y2. Okay, so let's type that in. 10,000 and then 5,000 times 1.0625 raised to the, it has t, just use your variable button. The variable is going to be x, but the x can be t just the same, so that won't really matter. So I've got my two functions typed in. Now here's what we're going to attempt to do. Let me try and draw this here on the paper first so that you can see kind of what exactly we're after. We're going to have a first quadrant graph. We're going to make two lines. We're going to have the y1, which is going to be a horizontal line here at 10,000. And then we're going to have a y2, which is this exponential model doing this sort of thing. Okay, so there's my y2. And right here, where they intersect, is some t value. Well, it just happens that that's the t value where this curve is equal to $10,000. That'll give us the time that we're looking for. So we're going to produce this graph on our calculator and attempt to find where those two lines intersect. Now, if I just push graph right now, you'll notice that on your calculator you get a screen that doesn't show you anything. And that's because the normal scale on the graphing calculator goes -10 to 10 and -10 to 10. And we're dealing with dollar amounts that are in the thousands. So we need to change our window. So I'm going to hit my window button here. And the y values are these dollar amounts here. And they say -10 to 10. I just need a much bigger maximum, like say 15,000. And something bigger than my biggest value there. I don't know about the time yet. The time, the t is the x's. I do know for certain that time can't be negative, so maybe we can just take that negative 10 off and make it 0, and let's see what that looks like. And we can see if they will cross yet. In fact, it looks like with a t of 10, they don't intersect yet. So let me change my window and make the maximum value 20. And we'll see if they intersect. And sure enough, they do intersect. So what we want to do is try and find that intersection point. And here's how you're going to do it. Above the trace button right here, you can hit second trace to get into this calculate menu. The fifth one down there says intersect. That's the one you want. So now you see a little cursor that you can move the left and right arrows and go back and forth on. What you want to do is just get that cursor as close to the intersection point as you can, and once you're there, you just have to hit enter 3 times, and it's going to give you an X value where the Y value is 10,000. What you want is that X value. That X value that we want is our T value, and it is approximately 11.43 units are in years. Next example says the city population, which was initially 15,500, has been dropping by 3% a year. Write an exponential function and graph the function that models the population of the city. Use the graph to predict when the population will drop below 8,000. So let's start with our A of t equals little a 1 plus minus r to the t. The A of t then equals the initial population was 15,500. 1, we're going to use minus because the population is dropping. 3% is 0.03 raised to the t. So we have A of t equals 15,500 times 0.97 to the t. So there's our model. Now we want to use the graph of this model to solve the problem for when the population will drop below 8,000. So I want a final population of 8,000 here. And just like we did in the last problem, we're going to do this on the graphing calculator. We're going to let this side be the y1, this side be the y2. We're going to graph them and try and find an intersection point between those graphs to find the value for t. So let's bring our calculator back. I've cleared out the other functions, and let's go with this one now. The y1 needs to be 8,000. The y2 is 15,500 times 0.97 raised to the t or x. Before I hit graph, let's just think about the windows. The maximum y value needs to probably be bigger than the bigger of these two values here, so I'm just going to make it 16,000. The x maximum, the x is how many years it takes for this population to reach this value, and that I don't know. If I knew it, there wouldn't be the need for the problem. So I'm just going to leave it at 20, but that's purely a guess. If they don't intersect by 20, then I'm just going to come right back in here to window and I'm going to make that number a little bit bigger. So here I've got my 8,000 line. Here I've got my exponential decay line coming down towards the 8,000. Question is, are they going to cross before they get off the screen? And they do not. So we need a bigger x maximum, and probably not bigger by much. If I go like 35, I probably could do 30 or 40. There's no set right or wrong answer. I just need to be able to see where they cross. And I've got an x big enough that I can see that. So now we need to find that intersection point. And the steps again are to hit second, trace. You want number 5, intersect. You just bring that cursor right on top of the intersection point, as close as you can visually get, and just hit enter 3 times. And I've got an x value of 21.1 I'll just use 2 decimal places, 71 years.